And we're back. So actually, let me just double check that we're back. And we're back. So I was asking, how would we represent a negative value? That's an interesting question. So if you're anything like me, you had one particular approach, and that's probably the wrong approach. But everybody has that approach, so it's perfectly normal to not necessarily know the crazy, weird way that 2sComplement actually works. So my approach, I would normally poll the room, see what your approaches might be. And some people say, oh, use a negative sign. Well, there's no negative sign. And then, so the follow up is like, okay, we'll represent the very first bit, the most significant bit. We'll just have a bit in our binary number representing the negative sign. If it's a 1, it's a negative number. If it's a 0, it's a positive number. So it's a sign bit, essentially. Um, so if I have 0101, 0101 corresponding to 5, I can't put a negative sign in there to represent negative 5. So what if I put a fifth bit in there? I would have a 10101 representing negative 5 and a 00101 to represent 5. So essentially, whether I have that first bit on or off tells me if it's a negative or a positive. Um, or maybe I need to do some radically different other approach. So if I do a data bit uh, right here, this red these red numbers here, this would be positive 42 because I have a 0 there, and this is negative 42 because I have a 1 there. The 1 sign bit being it's negative, the 0 meaning it's positive. Great. Well, maybe not so great, because without that sign bit, I can represent I can normally represent 2 to the power of 7 possible values. Oh, sorry, 2 to the power of 8 possible values for 8 bits. With a sign bit, I can represent 2 to the 7 minus 1 positive values, 2 to the 7 minus 1 negative values, and I have 2 0 values. I got all zeros and a 1 with all zeros. They're both 0. They're not, so I have 0 twice, and I'm actually I only have one fewer number that I can represent. Instead of 2 to the power of 8 different numbers, I can represent 2 to the power of 7, 2 to the power of 8 minus 1 possible values. Right? I'm missing a value. So I have one less number I can represent. That's not shouldn't be the end of the world, but this 2 versions of 0 is a real pain. What's worse though is with that sign bit, I need to I need to figure out how to do the math differently. So normally when I do math, let's do some math here. I'm going to do 1 0 1. Put a 0 in the front. Okay, so what is that number here? That's a 1 2 4. That's our 5 again, right? That's positive 5. And I'm going to add 3. Add 0 1 1. So what do? Just the same as I would do with normal arithmetic. I'm going to add 1 and 1. That gives me 2. I can't represent 2 here. I have to do a carry. So I carry that over. Carry it over. This is 1 and 1 because the carried bit. So 1 plus 1 is 2. I have to carry it over. This is 1 plus 1, 2, and I have to carry over 1, 0. All right. So that's what 5 plus 3 is. By the way, what is this number here? That's 8. 5 plus 3 is equal to 8. Great, we're golden. Okay, let's try and do that with negative values. Well, what the hell do I do with a negative value? Right? If I have 5 plus negative 3, so let's put another zeros here at the end here, just to make sure we have enough bits. Okay, so 0, 0, 1, 0, 1. Negative 3 is 1, 0, 0, 1, 1. 5 plus negative 3, I'd expect the value to be true, 2. But now I need to figure out how to subtract things. The math is just going to get ugly as hell. And I need to know that first bit, I need to look at that first bit and go like, oh, it's a negative value. So now I'm going to subtract things off. And now I have to do carries. What if I could just do addition for all cases? Whether it's positive or negative, doesn't matter. I just do addition and it works. What if I could represent 2 to the power of 8 different numbers. And what if I didn't have to worry about negatives and positives at all and the math just works? And that leads us to von Neumann's second contribution, or third, depending on how we're counting this thing out. John von Neumann pointed out the fact that when you do modular arithmetic, you get something very similar to what we are actually looking for. And it gets a little bit wonky. So again, representing 0 to 127, negative 0 to negative 127, not ideal. Okay, and the maximum numbers we can represent is 0 to 2 to 5 versus 2 to the 8, 56 combinations. Okay, um, so here comes 2's complement. 2's complement, and this is not complement, it is not, that is a nice looking number system, that is a nice looking 2, it is complementary, as in it goes together. I, honest to God, in my 20s did not realize that those were completely different words in the English language, but they sounded the same. So complement versus complement, and they're very different. 2's complement is the two numbers work together to, based on powers of 2, to give you negative values. So here's how this is going to work. Let's take 13 plus x is equal to 0. If I were doing normal math, what would you say? What's x? Well, you'd say x is negative 13, right? So I can save it later, right? X is equal to negative 13. 13 plus negative 13 gives me 0. Great. That's what I want. That's what I expect with negative numbers. If I add it to the arithmetic complement of it, right? If I add 13 to negative 13, I get 0. Okay. So can I there's actually for modular arithmetic, there's a complement as well. So let's do that modular arithmetic thing. What is 13 mod 4? Well, that's going to be 1. If I take 13, I divide it by 4, I get 3, remainder 1. Okay, what's 13 plus x mod, what is x if 13 plus x mod 32 is equal to 0? What's x? Well, x is equal to 32 minus 13, right? Which is, I guess, 19. I hope. Yeah, it should be 19. Okay, why is it 19? Because 19 plus 13 gives me 32. 32 mod 32 is equal to 0. Right? 32 mod 32. If I divide 32 by 32, I get, it's evenly divided, it gives me 1 with remainder 0. If I added 20 instead of 19, I get 1 remainder. It gives me 33. 33 mod 32 is equal to 1. I can do this over and over and over again, and you'll get, there's a weird mathematical relationship. We're not going to go into the heavy details on this. I could spend entire lectures on that. What is y in this case? So this value right here, what is y? Well, what do I add to 31 to give me 0 when I mod 32? Well, I could add 33 technically, or I could add other numbers like that. But the easiest approach is I add 1. Y is equal to 1. 1 plus 31 mod 32 is equal to 0. Right? That's what we're looking for. The complement, the arithmetic complement mod 32 is always the other number, you add them two together, you get the main number I'm looking for, the 32, so that you get a 0 in the end. This is what we were talking about. This from a mathematical standpoint, where you don't have to get crazy on this. But when we were talking about having 8 bits and exactly 8 bits, that's essentially what we end up getting. If the maximum you can store is 256, it's effectively mod 256. So if I add numbers that are too big for that can be stored into those 8 bits, I overflow and I lose a bunch of my data. And that's what John von Neumann finds out or realizes really early on, that if I because there's a limited amount of precision, I can make it so that my negative numbers and my positive numbers work together to always give me the right number within that range. So if I add 1 and 1111 together, I will get 0 because here I go. 1, 2, 3, 4, 0, 0, 0, 1. There's exactly 4 bits. There's not a fifth bit, and if I try and go to the fifth bit, it just goes off into the ether. It just gets thrown away. There's a limited amount of precision that I have with a computer. If I'm at 4 bits, I'm only doing 4 bits. The numbers are going to be bigger than this normally. But if I'm pretending, if I this is the amount of precision I have. If I go beyond 4 bits, I throw away whatever extra numbers. So 1 plus 1, 2. So I have a carry. 2, I have a carry. 2, I have a carry. 2, I have a carry. That 1 gets thrown away. I put down a 0. And oh wait, I get 0 in the end. It's that fifth bit just gets thrown away. I can't store it anywhere. I only have 4 bits to store stuff. So it's like overflowing, like a pot overflowing, or whatever yeah, let's say a pot overflowing. You're adding water to it, and then if you go too much, it just pours over the top. Okay? The overflow just gets thrown away, and what I get left with is all zeros. That's the key to 2sComplement. I need to find a number that works with these two numbers work together to give me 0 when they're added up. So what I want to do is say this is, and I'll let the cat out of the bag here, I'm going to claim that that's going to be -1. So if I add 1 and -1 together, I get 0. I'm going to temporarily pretend that these 4 ones are -1. If I add the 1 and the -1 together, I should get 0. In this case, I would. How about this one? This number and this number. If I add them together, I will get 0 as well. So let's figure out what this number here is. This is 4. This is my 5 again. This should be -5. 1011 is -5. So if I add them together, 1. So 1 and 1. And that 1 gets thrown away. And I get all zeros again. Huh. There's always a number for all these positive values that we have. There's always a corresponding number here that when you add the two of them together, you get a 0. That's what 2sComplement is. So what we do here to get this, by the way, and we'll talk about this more in 2 slides time, is we're going to take the original number we have here, 0101. We will then flip all the bits. So in this case, 0101, our flipping all the bits would be 1010. Just blindly flip the bits. Just everywhere you have a 0, it becomes a 1. Everywhere you have a 1, it becomes a 0. And then we add 1. And that's going to be add 1 to this whole thing, so it's going to be 1011. Hey, that's -5. This just happens to be how the math works for us all the time. It works because of the mathematical foundations. And if you don't want to know about how the math works, that's fine. The negative value is always represented by flip the bits, add 1. Flip the bits, add 1. Flip the bits, add 1. It's not change the sign at the end, which some people try. They try all sorts of things. Just flip all the bits, add 1. Okay, so I wanted to break this into more pieces, but here's what we're doing. We have our original number system, right? 0 to 15. This is going to be 4 bits, right? We can represent 0 to 15 with 4 bits. This is 1, 2, 3, 4. This is 0, 0, 0, 0. All right. What if we just take and split it right down the center so that as soon as you get to 1, 0, 0, 0, everything with a 1 in the front is going to be considered a negative number. But it's kind of quirky in that respect. Okay. It's not just a sign bit, though, anymore, like we were doing before. Instead, we're going to have 1, 0, and again 1, 2, 3, 4. What we're going to do is take this entire chunk of numbers, all the binary representations, and instead of considering them to be 8, 9, 10, 11, 12, 13, 14, 15, it's still just a binary number. We're going to interpret this as -8, -7, -6, -5, all the way to -1. We're just going to take this thing and shove it on that end of the number system. The whole thing, just that entire chunk, move it to the back, to the other part of the number system. Because here's what we end up getting. If I add 0 and 8, I get 0. If I add 1 and 15, I get 0. I have 2 and 14, I get 15 mod. If I'm mod, just realizing it should be mod 16 everywhere. If I add 1 and 15, I get, and this will be still, this doesn't work at all, but that's fine. This is the weird one. 1 and 15 gives me 16. 14 and 2 gives me 16. 13 and 3 gives me 16. 12 and 4 give me 16. 5 and 11 give me 16. 6 and 10 give me 16. 7 and 9 gives 16, right? And when I do the mod 16, I always get a remainder of 0. If I add 1 and -1, I get 0. I add 2 and -2, I get 0. 3 and -3, I get 0, right? They exactly correspond. This 15 and the 1 and -1 exactly correspond. The results end up being this exact same. If I mod 16 or if I do negative arithmetic, I will get the same values. So what I'm going to do is pretend that these higher number binary these higher numbers from 8 up to 15, I'm going to just pretend they're negative values. It's still just zeros and ones. My interpretation is different. I'm not changing anything. The binary numbers are the same. The math ends up being the same. My interpretation of it is different. So this is all I'm going to do is I'm shifting this entire set of numbers over to the left-hand side, pretending shifting it, just pretend shifting it over to the other side. And when I do the math just happens to work now. So you can take it on blind faith why the math works, or you can try and figure it out on your own why the math works. One of them is using normal arithmetic. The other one is using modular arithmetic. The modular arithmetic, since there's a limited amount of precision that we have, we automatically get this overflow, and the math still works the way it did before. And now I don't have to worry about positive and negative numbers. I just add, 001, 1001 to whatever the value for 2 is, add those two numbers up, I'll get the right answer. Whether it's positive or negative, it's still going to end up being the right answer. Okay, so again, the approach is flip the bits and add 1. So I have -5. What is -5 as a 4-bit 2's complement number? Then we're going to look at -6 as a 4-bit 2's complement number. Then we're going to look at -5 as an 8-bit 2's complement number. Okay, so here's our approach. I'm going to have, this is 5 as a binary number. I'm going to flip all the bits. It's 1010. So that's my flip step from here to here. From 0101 to 1010. I just flip everything from a 1 to a 0, 0 to a 1. I then add 1. I get 1011. That is -5 as a 2's complement binary number. All right. Here is 6. It's 0110 as a binary number. I flip everything. I get 1001. I add 1. Notice if I add 1, this 1 plus 1, I cascade over to the next one. Right? This, after I add 1 to this, I have to move the bit over, and I get a 1010. Right? Hopefully I'll try and write it out a bit more clearly. Carry 1, which is why we get what we have. Okay, that is 6 as a 4-bit 2's complement number. Let's try an 8-bit 2's complement number. Again, the number of bits is critically important. It's not arbitrary. I can't just pretend I only have 3 bits or something like that. I need to know. I cannot answer this question. If I do not tell you how many bits I have in the number, you cannot show me what the negative value is. It makes no sense if you do not tell me if I do not tell you exactly how many bits I have. So, as an 8-bit 2's complement number, here is 5 as an 8-bit number. Notice it looks exactly the same as the original 5. I just have a whole bunch of zeros at the front, right? These are just, you know, stuffing zeros. They're just little extra zeros at the front because it's 8 bits. I need to use all 8 bits. I'll put zeros in there if they're not already there. I'll put zeros in to fill in whatever spaces that were left. Okay, I flip all the bits. 1, 1, 1, 1. Okay, well, I got a whole bunch of ones now. What the heck? And then I add 1. I get this. It is a different number between this. This and this are not the same number anymore. Negative 5 as an 8-bit binary number is not the same as negative 5 as a 4-bit binary number. They're represented differently. They're not the same number. And that's what's really quirky about 2's complement. You need to know how big the box is that you're storing this stuff in. Okay. This is one of those things that you need a lot of practice playing around with. So just try it out. Make sure you feel a bit more comfortable. Right? Here's how a 4-bit 2's complement would work. It goes 0, 1, 2, 3, all the way up to 7. And as soon as you get to 1, 0, 0, 0, it's negative 8. Then negative 7, negative 6, all the way to negative 1. Let's try a couple of these things. I normally say this as an exercise, but let's try what's negative. Let's try negative 1 as a, what is negative, by the way, the flip and bit add 1 also works for this. So 2, 3, 4. If I flip all the bits, I get 0, 0, 0, 0, plus 1, I get 0, 0, 0, 1. Hey, wait, I can go from negative values to positive values to negative values. The interpretation. So if I say, here is the number negative 5, or here is the number negative 13, it'd have to be an 8-bit binary number. What I want to do is figure out what 13 is in binary, then flip the bits and add 1, and that will be negative 13 in binary. So I think we have an example of this. But notice how the number system works. As soon as I get past 7, it becomes negative. And that's why we have to learn about this. Because if you're dealing with an integer, or an unsigned integer, for example, and you happen to add a number that's too big, makes this too big, suddenly you get a negative number when you did not expect it. You go from, some really, really big number, and then bang, it becomes this really, really big negative number just by increasing 1 by 1. And if you don't know what's going on under the hood, it just seems like witchcraft. It's just crazy. Like, you added 1 to this ridiculously big number, and suddenly it becomes this ridiculously big negative number, and you have no idea why. Because under the hood, that's how it's interpreting the numbers. That's how the numbers are working. And it happens more times than I care to count. I want to see if I have a quiz in here. But your take-home lesson for this is, effectively, here, the bits are the same, whether it's signed or unsigned, whether you have negative numbers or not. The binary underneath it all is exactly the same, whether it's all positive or it's positive and negative values. My binary is the same. How I interpret that number, or how I interpret that binary number, tells me what it looks like. If I say it's a character, well, I represented it one way. If I say it's a negative value, I represented it a different way. The interpretation changes of the bits change, and therefore it's equivalent to two languages having the same word in it. The word is exactly the same in both languages, but how you interpret what that meaning of that word is radically different. I have some very embarrassing stories about speaking French and saying the wrong word and saying things that are really not very nice words. It's kind of dirty words by accident when speaking French, just because I use the English word and it does not translate the same into French. Yeah, I won't give you the example. Anyways, C++ and C, though, are famous because they just merrily let you interpret the data any way you want. You could take a negative number and say, no, 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 it's positive, and it will just interpret it as a positive number. And that is why we have to learn this, because if you don't know how that's working, then C is impossible to try and debug afterwards. Okay, so if I want to figure out what 4 is an 8-bit binary number, what would I do? Let's do 28, negative 28, just to see what happens there. And then what I'm going to do is I'm going to leave the quiz, because we're going to see what negative 28 is, but practice with negative 4 first. We're going to see what negative 30 plus negative 28 is going to be. I'll give you a hint. When you've calculated this one, you've also calculated the next one. Subtraction is the same as adding a negative, right? In normal mathematics, same here. So instead of having to have a separate thing for negative numbers, or have a separate set of calculations in the computer for actually doing subtraction, I actually don't need that. All I do is I add the 2's complement. I add the negative version or negative implementation of that number, and I get subtraction. The compiler, at no point in time do you ever need to do subtraction in binary. You only need to learn addition and multiplication to get that. Um, so also take a look at what happens when with 4 is a 2's complement number. We've already looked at what it looks like. It's all ones. What about negative 8? How do we get negative 8? Let's go over that one first. So how do I do negative 8 as a 2's complement number? Well, I would need to represent as a 4-bit 2's complement number. What is 8 as a 4-bit 2's complement number? Oh wait, I can't do it. Honestly, I can't do it. What is 8? It is 1, 0, 2, 3. Yep, there you go. That would be normally what I would represent 8. But remember, this is, I can represent up to 7. So this is actually not the number 8 at all. This is, well, this is actually a negative value of some 4. It's actually negative. This is negative 8. What if I do the flip and add 1? So I find this a fascinating thing here. Maybe I'm a nerd. I'm guaranteed I'm a nerd, but maybe you're not as interested as I am. Let's take this number. I'm going to flip it. So I'm going to say 0, 1, 1, 1. Plus 1, what do I get? This will cascade to this will cascade to this, and this will go over here. So I get plus 1 gives me 1, 0, 0, 0. What the hell? When I flip the bits and add 1, it's reflexive. It's reflective. As in, I don't get a negative and a positive version of it. I only get the same number I started with. Why? Because I can't represent negative 8. I cannot represent 8 as a 4-bit 2's complement number. My numbers go from negative 8 to 7. That's my range in 2's complement numbers. I actually miss a number on the far end, which is kind of weird, but I still represent 16 different numbers here. Negative 8 to 7. That's where 2's complement is kind of quirky. This is something to play around with and make sure you get some practice with. Okay, let's try 28. So how do I do 28 as a 2's complement, 8-bit 2's complement number? Well, first of all, I need positive 28, and then I'll flip the bits and add 1. So what's positive 28? Well, let's see here. Let's do the most significant bit version of it. There's going to be a 16, and then I'll figure out the rest. So let's do 28 minus 16 is equal to 12, right? Please say I'm right on this one. 12 minus 8 is an x power of 2 that we have there, and that's going to be equal to 4. 4 minus 4 is equal to 0. Okay, so what I'm going to have is the 16, 8, 4, 2, 1. I'll put a 32 in there as well. 0. I'll need more than that. So let's just clean it up. Okay, I have a 16 that was on. I have an 8 that is on. I have a 4 that is on. I have a 0 and I have a 0. Thus, I need 8 bits. 1, 2, 3, 4, 5. I need 3 more. 0, 0, 0, 1, 1, 1, 0, 0. That's what 28 is in 8-bit binary. Okay. flip my bits. 1, 2, 3, 0, 0, 0, 1, 1. Oh boy, this is going to cascade out. It's going to be this goes to this goes to this. So I'm going to get 1, 2, 3, 0, 0, 1, 0, 0. I want to do that. All right, that's negative 28 as a binary number, as an 8-bit 2's complement binary number. 1, 1, 1, 0, 0, 1, 0, 0. Let's double check to make sure that we're doing it right, but yeah, it seems right. And now that I have that, if I calculate what 30 is, and I add negative 28 to 30, what do I get? Okay, notice that our range here is we actually have one less number. It goes from negative 2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. So negative 8 to 7. 2 to the power of n minus 1 is 8. 2 to the power of n is 16. 2 to the power of n minus 1 is 8. Minus 1. So I have the same range, the same numbers that I can hold. 8 bits goes from negative 128 to 127, for example. I have a better range. I don't have two zeros. And the math can be done really quickly because I don't have to do subtraction or figure out if it's negative or not. I blindly add two numbers together. The same way, whether they're positive, negative, or whatever the case is. Everything works as you expect because of this system. And this is a beautiful, there's no equivalent to this system in floating point numbers, which we'll get to and briefly touch on next. But this is why people, I think it's an absolutely gorgeous or really interesting system for how to do arithmetic. Once you get it in your head, it'll all make sense. But you need to do a bit of practice to make it your own. Because I can talk all I want, but you need to do a bit of practice to make your own. Try 30 plus minus 28 and see how well you do. And then maybe try what negative 30 is as a 2's bit for what the value is as an 8-bit 2's complement number. Try out some various numbers and see how things work for you. Okay? Okay. So when we come back, we're going to be looking at floating point numbers. Thanks, everyone.